following are sets of scores in different tests. Calculate the mean and the standard deviation. So we've got the set 1, 4, 5, 10, 7, 5, 6, 4, 3, 9. And then we've got 3, 4, 5, 3, 6, 4, 5, 6, 4, 7. Now, the important thing to realise is that the mean is a measure of central tendency, and the standard deviation is a measurement of how the data is spread out. Just looking at the data, this data here looks more spread out than this data here. But we can actually show that by calculating a statistic. Now, the other things that you might have come across already about spread is the range, or the interquartile range, or even perhaps the semi-interquartile range, which is the one that really equates to standard deviation. So, finding the mean, the x bar is sigma x over n, so you need to add up all the values and divide by the number of values, which is 10, and that gives you 54 over 10, which is 5.4. For the standard deviation, we're going to need to write down all the numbers down the side, and what the standard deviation does, it works out how far each measurement is away from the mean. So we do 1 minus 5.4, which is 4.4, minus 4.4, 4 minus 5.4, which is minus 1.4, 5 minus 5.4, and 0.4, and then so on. But the problem is some of these are negative and some of these are positive. So to avoid that problem, because if we were to sum these up, we will they will cancel each other out. So to avoid that problem, we square each one. So we're squaring each of these numbers here. And then what you do then is add those up. And we say that the standard deviation is the sum of all x minus x bar divided by x bar all squared. This sum, it means add all these up, so it's 66.40, this value, squared divided by the number of items. So, in this case, ours will be the square root of 66.40 over 10, which gives me 2.57681, which gives me 2.582 significant figures. However, if this data was taken from a larger set of data, then a better estimate of the actual standard deviation is to use what's known as the unbiased estimate of the standard deviation, or sometimes known as the sample standard deviation, where instead of dividing by 10, you now divide by n minus 1. And this is the one which is used in the current A-level syllabus. So, Sn minus 1 is going to be the square root of 66.40 divided by 10 minus 1, which is 2.716. So this is like a better estimate of what the standard deviation would be for the population. Now, it can actually be proved using expectation algebra that this is actually true, but it's beyond the scope of this particular course. So this is the one that we're going to use in the A-level course. That gives me 2.72. Now, for the second set of data, we do exactly the same. We find the mean, we add them all up, and we divide by the number of values. We get 4.7. The standard deviation, again, we make our table, work out how far each way is away from our new mean, 4.7. So the mean of both sets of data is fairly close. But if we work out how far they are away from the mean, and then obviously square them, and we square root at the end because we've squared. So we're taking the average of how far each thing is away from the mean, but we square in order to not cancel out data. So the population standard deviation will be 16.10. You see that's a much lower number than what we got before, divided by 10, which is 1.26885, which is 1.27. But using the unbiased estimator, Sn minus 1, don't forget to take away the 1, we need to do 16.10 at 10 minus 1, which is 1.337, which is 1.34. This number is normally slightly a bit higher than this one here, but this is one that we're going to be using to calculate at A level. Note that the first data set is more spread out than the second one, and perhaps would be more better if I was going to rank the students, because if I'm ranking the students I want a quite wide range of data. Right. Alternative forms of the standard deviation. Now this is a proof, it's not required for the A-level course, but it's quite interesting to do. So if we expand this, we're going to get x squared using our spelling a minus b all squared, minus 2x x bar plus x bar squared divided by n. And so that gives me sigma x squared over n minus 2x bar. Now, because we're just summing the x's, sum of x bar over n, but we've still got the sum of x bar squared over n, just to bring it out the denominator. Right, so we're going. This becomes the sigma x over n becomes the mean, and how here we're doing the mean. We're summing the mean n times. We're adding up the mean squared n times. So we can just write that as n x bar over n. Obviously the n's cancel out, and therefore we get 2x bar squared from there, and then just plus x bar squared, and we'll end up with this formula, sigma x squared over n minus x bar. However, for the unbiased estimate, we need to multiply this by n over n minus 1. So we do n over n minus 1 sigma x squared over n minus x bar squared, which gives me sigma x squared minus n x bar. So the n will cancel. The n will cancel out here, and then we're going to have the n here, but it will all still be over n minus 1. So the unbiased estimate is written this way, sigma x squared minus n x bar squared over n minus 1. And this is a more easier formula to use than the first one, so this one should be remembered. Or Sn minus 1 will be the square root of Sxx. Now Sxx is just what the top bit is, over n minus 1, where Sxx will be sigma x squared minus n x bar squared. Now this value is actually given on some calculators. Okay, so this is the one that we're going to be using at A level, so this is the one that we need to remember. So, going back to our numbers using the different method, because the only thing you have to calculate from x when we're doing this method is x squared. So, our population standard deviation will be sigma x squared over n, so that's going to be 358 over 10 minus 5.4 squared, taking the square root, which is 2.57681, which gives me 2.582 significant figures. But using the one that we want, the unbiased estimate, so we can just put the numbers in. Square root of 358 minus 10 times the mean squared over 10 minus 1 gives me 2.716. Notice we're getting 2.72. We're getting the same numbers we got the first time through it, so it sort of verified the result. And for the second set of numbers, x bar was 4.7. We list the numbers down here. We square each of those and sum this column here. So it's going to give me the population standard deviation to square root of 237 over 10 minus 4.7 squared, which gives me 1.26885, which is 1.27. And then using the unbiased estimate, we're going to get 237 minus 10 times 4.7 squared over 10 minus 1, which gives me 1.337, and we get 1.3423 significant figures. Now, these values can actually be found from a calculator. So if you're using a calculator, then in the spreadsheet mode, you need to put down the numbers of each one here. So this is set A and this is set B. and then you can get the calculator to come up with the values that you need. Alright, so using this, so this is the value of the standard deviation that we particularly want. For the first set, again, we're not worried about that, and then for the second set as well. So we've got both sets of data here. Okay, so there's been a video to show you how to use the how to find the unbiased estimate of the standard deviation, or find the standard deviation from a set of numbers for the current A-level course. I hope you've understood, and I thank you very much for watching.